Hello, I'm Nishil, and in this video, I'm going to talk about our paper called Prodigy that addresses the memory latency problem in irregular workloads. This is a collaborative work with my colleagues at the University of Michigan, Wisconsin-Madison, at Edinburgh. Let me start by asking this. Did you know that in 2020, each person every second generated about 1.7 megabytes of data? That is about 2.5 quintillion bytes of data on an entire day. But wait, what's a quintillion? Hmm. Our natural reaction is to Google this, and while we do get our answer conveniently, what we don't realize is that there are about 3.5 billion Google searches done every day. Additionally, Facebook, Gmail, and Twitter process such large amounts of data too. This requires massive processing power, and to meet the needs of this ever-growing data crunching tasks, we need to optimize our computing systems as computer architects. In this spirit, we analyzed a variety of workloads from graph processing, machine learning, and scientific computing domains to better understand their execution bottlenecks. Profiling them on a CPU, we found that about 3/4 of their execution time is just spent on waiting for DRAM stalls, which cause a major and serious bottleneck in these workloads. And there are two reasons behind it. First, they exhibit irregular memory accesses, for example, A of B of I type of access. And second, these accesses are done over a large memory footprint. We classified the LLC misses of these workloads and found that more than 95% of these misses are caused by irregular memory accesses, which are costly both latency and energy-wise. Several prior works have addressed this problem, and a subset of prefetching works are shown here. We observed that there is a tension between complexity and generality. That is, some are limited to a subset of irregular memory accesses, versus others incur high complexity for generalization. Taking this as a motivation, the goals of this work are twofold. One is to prefetch for all key irregular memory accesses, and the other is to enable this at a low complexity hardware cost. We achieve this in our paper by proposing a specialized contract between software and hardware. A combination of software techniques such as compiler tools are used to gather program semantics, which are then passed to hardware for prefetching. As a result, Prodigy enjoys significant performance and energy benefits at a negligible cost. With this setting the stage, this is the outline for the rest of my talk. And now let's have a look at Prodigy programming model as a part of our software proposal. First, let's have a look at what these irregular memory accesses entail. We investigated a wide range of irregular workloads and found that two types of specific data-dependent indirection patterns are prevalent. We named them as the single-valued indirection and range indirection. Single-valued indirection is a B of A of I type of indirection where data from one data structure is read to index into another data structure. An example utility of this indirection type is to access vertex property in graph processing workloads. Range indirection, on the other hand, uses two values from one data structure to index into a series of elements into another data structure. This indirection type is used majorly to access vertex neighbors in graph analytics. Our investigation of these workloads also revealed that these fundamental indirection types are present in arbitrary combinations in these workloads. For example, workload A, that is like the BFS algorithm, uses a single valued indirection followed by a range indirection, whereas workload B, which is similar to a page rank algorithm, uses a range indirection first, followed by a single valued indirection. To capture this arbitrary existence of indirection patterns in real workloads, we propose what we call as a data indirection graph or a DIG representation. Data indirection graph is an abstraction of program semantics that captures how a workload's data structures are laid out in memory and how they're traversed by an irregular algorithm. A data indirection graph is a directed weighted acyclic graph that acts as a contract between software and hardware. Its job is to collect algorithmic information from software and communicate it down to hardware. The nodes and edges of a data indirection graph represent data structures and indirection patterns respectively. For example, for a C of B of A of I type of access pattern as shown on the left hand side of the slide, there are three nodes to represent three arrays A, B, and C, and two edges in its indirection graph. Node information includes data structure shape and size, whereas the edge information includes a weight that represents the type of indirection between them. The next discussion is about how to construct this data indirection graph in software. And one simple way to do that is by adding programmer annotations. Assuming a workload A and its data indirection graph on the left, a programmer can simply add API calls in the source code to construct a DIG. For example, register node and register edge calls are used to register nodes and edges of a data indirection graph, respectively. The input parameters to these calls are the metadata associated with DIG nodes and edges. While programmer annotations would do the job, sometimes the workloads are just way too convoluted and it requires domain expertise to annotate them. To lift the burden from a programmer, we also propose a compiler analysis technique that automatically constructs a data indirection graph in software. Our technique takes an unmodified workload as an input, analyzes the workload, and outputs a workloads binary that already contains a data indirection graph representation. There are two steps involved in our compiler analysis. In the first step, an intermediate representation or an IR of a workload is analyzed to find the existence of indirect memory access patterns. This information is gathered in the second step along with resolution of the relationship of dig nodes and edges and placement of API calls to construct a data indirection graph into the program binary. Finally, in order to write a data indirection graph information to hardware, a runtime library is used that converts these API calls to a bunch of store operations and eventually to write those to Prodigy memory units. This is the end of Prodigy programming model. And now let's have a look at how Prodigy hardware uses this DIG for prefetching. Before going into the hardware design, let me introduce a couple of key terms here. Assuming a workload's data indirection graph and data structures shown here, all dependent addresses that are accessed based on each other's data are set to form a sequence. For example, based on A of 0, B of 1, and then C of 0 to 2 will be accessed. Hence, they all form a sequence. A sequence that is demanded by the core is called a demand sequence, whereas a sequence that is being prefetched by Prodigy is called a prefetch sequence. With that in mind, let me introduce the prefetching hardware components. To store a workload's data indirection graph, node and edge tables are used. These tables store key metadata information to identify a dig node or edges for prefetching purpose. Additionally, as seen in the previous slides, a typical workloads prefetch sequence can range multiple data structures and indirection levels. To keep track of live prefetch sequences and to issue non-blocking prefetches, we introduce the concept of what we call as the prefetch status handling register, or a PFHR file. In addition to these storage structures, Prodigy also uses simple control logic to issue prefetches, as we'll see next. Putting all of these concepts together, let's finally have a look at how Prodigy functions. For simplicity, I'm going to use the single core system with a cache hierarchy and DRAM for demonstration purposes. Microarchitectural events at different times will be annotated on the timeline and on the green action board. At t equal to 0, we assume that the data structures are already populated in memory and the caches are cold. And for illustrative purposes, I have annotated the data values to be part of either a demand or a prefetch sequence in different colors. First, the core issues a load operation to A of 0 to initiate the algorithm. Prodigy observes this load operation by snooping on the address bus between the core pipeline and the L1 data cache. Given that Prodigy initiates prefetching from array A, that we also call as the trigger data structure in the paper, a prefetch sequence is initialized upon observing a load to A of 0. This is the first out of two steps of prefetching that we call as the prefetch sequence initialization. Now let us zoom into the internal workings of Prodigy and we'll visit back this system level view in a later slide. To initiate a prefetch sequence, first, a load to a trigger data structure that is array A is observed. Then a prefetch address is calculated by adding a fixed lookup distance to the address of an observed load. The rest of the information about array A, for example, data element sizes, are obtained from the node table. Once the prefetch address of A of 2 is calculated, a prefetch request is issued and a new PFHR is allocated. And just as a reminder, the PFHR is allocated to keep a track of live prefetch sequences. Jumping back to a full system view now, after a certain amount of time, we assume that the cache fills for both demand and prefetch cache lines are received. And, and out of these, the demand cache fill is consumed by the core to further the algorithm as shown in the figure. The algorithm progresses by sending a load request to B of 1. The prefetch fill, on the other hand, is used by Prodigy to advance a prefetch sequence. This is the second phase of prefetching, which we call as the prefetch sequence advance. Going back into observing the internal Prodigy operations, the following steps are taken. A prefetch fill is identified by checking an outstanding prefetch address field in the PFHR file. Upon receiving a prefetch fill, an existing PFHR is freed. Edge tables are accessed to find an existence of single valued indirection between arrays A and B. And based on this information, as well as the data value read from a prefetch fill, a new prefetch address is calculated. This new address of B of 3 is issued for prefetching and a new PFHR is allocated. PFHR allocation continues until a leaf node of a data indirection graph is reached, that is the array C in this figure, after which there is no need to track a prefetch sequence as it terminates there. Going back to a system level view, The demand and prefetch sequences progress in tandem, and the hope is that in the steady state, most demanded data are already present in the cache because of prefetching, and they can be serviced at a much lower memory latency. So far, we've only talked about what to prefetch. Another important question to ask is when to prefetch. To make sure Prodigy always prefetches useful data ahead of the core, we use two techniques called the selective prefetch sequence drop and multiple prefetch sequence initialize. More details on these can be found in the paper. Now, after introducing the core hardware software proposals for Prodigy, let's have a look at how it performs. We evaluated Prodigy using Sniper Multicore Simulator by modeling a three-level cache hierarchy. We used non-prefetching baseline and three state-of-the-art prefetching approaches to show the effectiveness of Prodigy. A variety of graph processing, linear algebra, and scientific computing workloads are used for evaluation. This slide shows that Prodigy outperforms a non-prefetching baseline by 2.6x on average. This speedup is mainly attributed to the improved memory latency and the reduction in DRAM stalls by more than 80%. As a side effect, Prodigy also improves the stalls caused by branch mispredictions. And this is because several branch outcomes depend on the load values. As shown in prior works, acquiring loads at lower memory latency improves the penalty of branch mispredictions as they can be resolved earlier. Prodigy also improves the overall energy consumption of a non-prefetching baseline by 1.6x on average. This improvement is mainly attributed to the reduction in static energy as it is proportional to the workload execution time, and speeding up workloads result in saving in static energy consumption. Here, we compare the performance of Prodigy with three state-of-the-art prefetching baselines. The performance of the baselines are chosen from the best reported speedups from the respective publications. The speedups are then averaged over commonly evaluated algorithms to Prodigy, and the same methodology is also applied to obtain the performance numbers for our approach. The figure shows that Prodigy outperforms state-of-the-art baselines. And this is because, number one, Ainsworth and Jones graph prefetcher targets BFS type access pattern that does not generalize very well to other irregular workloads. While a general purpose extension of their work was presented at ASPLUS 2018, unfortunately it incurs significant complexity. Number two, droplet only prefetches for a subset of data structures. And number three, IMP only prefetches for single value indirection. Therefore, Prodigy covers more indirect memory access patterns compared to both droplet and IMP. These impressive performance energy improvements are made possible by Prodigy at a minimum hardware cost. In total, Prodigy only uses zero point 0.8 kilobytes of storage space. And this compact design is mainly possible because of the data indirection graph that efficiently communicates this program semantics from software to hardware. For more evaluation results, please check out our paper. Finally, to conclude, data-indirect irregular workloads are used in several important application domains, such as search engines, social networks, recommendation systems, etc. And these workloads are severely bound by memory stalls. In this work, we introduced Prodigy, a hardware-software co-designed solution to improve the memory performance of irregular workloads. We showed that Prodigy enjoys the significant performance and energy improvements at a negligible area overhead. And finally, we believe that designing such specialized hardware software contracts, such as the data indirection graph, is an attractive approach to optimize system design moving forward. With that, thanks for watching.